Hello everyone. I'm Gitanjali. I'm a PhD scholar from IIT Delhi, and I'm also a TA for PMRF TA for this course, which is Introduction to Laser, which is taught by Professor Amar Sinai from IIT Delhi. So during each live section, um we'll go through the weekly concept and uh, and we will discuss the problems or doubts you must be having for the weekly assignment, as well as for any kind of uh, conceptual doubts or uh, any problems or any doubt in any of the steps of the slides or any kind of doubt we'll discuss during the live section. And besides that, if possible, then I will also solve some few additional problems that will help you to understand the and also understand the concept, as well as to get some additional problems so that uh, you can get a practice of the problems with solution. Okay, so without further delay, so let us get started. So in last week, we were talking about week 8 concept, and we haven't covered all the concept. So today I will start with week 9 concept first, so that whatever doubts you must be having in the week 9 concept, that will be clarified first. Then I will cover whatever was there and whatever that were uncovered in the last live section. So first we'll go through the week 9 concept first. So before that, let me ask whether you have any doubts in the week 8 assignment solution, because the solution has been released. You must be seeing the solution. So if you have any doubts in the week 8 assignment, then you can ask me now. Otherwise, we'll start with week 9 concept. So in between, let me start the week 9 concept. So in week 9, we discussed about what are the laser output characteristics. So laser, as we have already seen, it consists of a pump and a active medium, as well as a optical resonator, which acts as a feedback medium. So if you see this figure, these are there is a pump which is used to excite the active medium. And there are two resonator. One is mirror M1, which is reflectivity 100%, and another one is a mirror M2 with reflectivity 90%. So in between these two mirrors, the light will oscillate, and certain amount of light will uh, it will emit through this mirror M2. And at steady state, what we have seen, the gain in the amplifying medium is exactly compensating the losses in the system. That is, at steady state, gain is exactly equal to loss. Okay. So in summary, laser is nothing but a optical amplifier with a resonator. And optical amplifier, it mainly controls the P output power through the mirror M2. Hence, it also controls the intensity. As well as the resonator, it controls what will be the monochromaticity and how diverse the beam will be, how directional the beam will be. Okay. And these are some schematic of what is the procedure that happens whenever you pump a system. Like at time t equals 0, you initialize the pump. So you excite the active medium using the pump. So what will happen initially? So initially, if you recall, the ground state population is more than the excited state population. So if you take a three-level system, which is shown in this figure, and if N1, N2, and N3 is the population density, then we have seen the ground state population N1 is always greater than the higher state population. So what will happen initially? So initially the pump will excite the atom from the assignment 8 question 7. Okay. Okay, so let us see the problem first, then we'll start with the laser oscillation. So let me see. So give me some time so that I can open up the question and go through the problem. Mm, Question 7 and 6. Mm, Okay, so it's a numerical problem. So can you tell me what is the doubt you are having in this problem? You are already unmuted.
या
Okay.
मैम जो क्वेश्चन नंबर 6 है
Hmm.
इस मैम जो एक्चुअली में यहाँ पे 2 डेसिमल तक पूछा गया था
Okay.
और जो आंसर दिया गया है वो 0.56 टू 0.76 और थ्री
Okay.
डेसिमल के लिए आप जो आंसर दिया गया था 0.769। तो क्या मैम ये गलत ही कंसीडर होगा क्योंकि 2 डेसिमल तक पूछा गया था।
Okay, so you got a answer around 0.769, then you round it off to 0.77, I think.
या
Okay, no, it's not correct. If it's not incorrect if the procedure, if you are getting 0.769 using the, so in between you must have done some approximation, right?
या
Like
मैम
you have must have rounded off some digit in between. Okay, okay. I think in the discussion forum also one
या
student have asked the same one. So, okay, not a issue. We will go through the problem again, and if the procedure is correct, and I have also saw the procedure, it seems to correct. So let us give some time so that we'll update the answer or of question six.
ओके
So I will talk with them and let us let you know in the by announcement or in by writing the discussion forum.
ओके मैम मैम क्वेश्चन नंबर 7 में सर ने पढ़ाया था ऑलरेडी डिस्कशन फोरम में रेज भी किया गया है कि सर ने 0 टू d की बात की थी और यहाँ पे ऑप्शन हम लोग उसी हिसाब से 0 टू x के उसमें लिया था और यहाँ पे -x टू x का जो ऑप्शन है उसको
Got it, got it. This also have been asked in the discussion forum. Got it, got it. So if you take x from 0 to x, then you will get four minima in the same line. But if you take x minus x to x, then the two will come one side and another two will come other side. So it's like it's confusion between B and D, I think. So this I will also ask about this question because it is also seems to correct. There is no issue कि B and D are not correct. So let me talk with them and let you update. Okay.
ओके थैंक यू
Hmm. Other than this, any other doubt?
नो मैम
I- Okay, then let us start the session. So, okay. So initially, when we pump the system, what will happen? The spontaneous emission will start begin because initially there is no population inversion in the system. So spontaneous emission will begin whenever you pump a system in time t equal to 0, and after some time, the spontaneous emission will repeat again and again after again. But when what will happen after some time? The population in the ground state. It when time t increases, what will happen? The population it gradually decreases. That is the ground state population. So what will happen at a particular time t2? What will happen? The population inversion is start to we achieve a population inversion in the system. So in this condition, what will happen? Whatever the light that is getting reflected from this mirror, so this light will initiate the stimulated emission process. So whenever the population inversion is satisfied, the reflected light, it will initiate the stimulated emission. And after some time, the stimulated emission, it will dominate over the spontaneous emission. And over time, we'll see a steady state laser oscillation because we will see that the gain of the medium will be the losses in the system will be compensated by the gain in the system. So this is the formal procedure that happens whenever you pump a system. So initially spontaneous emission will begin, then gradually the stimulated emission will begin, then it will dominate, and over time we'll see a steady state laser oscillation. So this is the general procedure. Next, what we have seen. So these are the things that we have seen in our first live section. That is, now we'll see in more details what does this mean, how these characteristics, how these laser characteristics, these are related to the practical laser system. So one thing we have seen, one of the unique properties of a laser is monochromaticity. So monochromaticity. Uh, So it means, so by definition, it means single color or one wavelength or one frequency. But in practical system, we don't have any sources that have single color that emits at single wavelength or single color or single frequency. So to define for the practical system, to define its monochromaticity, what we define a parameter delta lambda. So delta lambda, it defines what is the extent of monochromaticity. So delta lambda by definition, it defines the full width at half of the maximum. So let's say we have a spectrum like this. So to define what is the monochromaticity of this mirror, of the source, what we'll do, we'll calculate what is the delta lambda of this spectrum at half of the, let's say it is I0. So we'll calculate around I0 by 2. So this delta lambda defines the chromaticity of the system. And we have seen two examples of two source example. Like one is the tungsten lamp, where if you see the spectrum, the spectrum of tungsten lamp, it is like this. So if you see, it is the delta lambda for this source is around 800 nanometer. And other than this tungsten lamp, if you consider a color filter, so color filter we have used, you must have seen color filter in your day-to-day life. So for the color filter, the delta lambda is around 50 nanometer. So you can see how monochromatic this color filter is comparison to the tungsten lamp. Now, and these are some typical example of color filter. Like we have different types of color filter: blue, green, red, violet, any color that we want to use. And for this color filter, the delta lambda typically lies between 30 to 60 nanometers. Another type of source that we have seen in our lab experiment, that is sodium lab. So if you recall the Newton's ring experiment, so we use sodium lamp to find out what is the wavelength of the sodium source that we are using. So if normally we report the sodium lamp wavelength is lambda equal to 5893 angstrom and with a delta lambda of 6 angstrom. But if you see clearly, the sodium lamp has two lines. One is D1 lines and D2 lines. So these are two spectrum that we have seen in the sodium lamp. And the separation between them is 6 angstrom. So if you see the actual wavelength where the sodium lamp emits is one is 5890 angstrom and one is 5896 angstrom. And each wavelength has the line width around 0.01 angstrom, which is much less than the color filter line. Now, from the sodium source, if you move to the laser source that we have seen in the single slit experiment, if you recall, then we use laser source for that. Helium neon laser we typically use. And for this source, the delta lambda, if you see, the delta lambda is much less than 0.000001. So you can see how narrower and how monochromatic the laser source are. So it is almost perfectly monochromatic. So delta lambda of if tungsten lamp, it is around 800 nanometer. So we have seen we use in a day-to-day life. And color filter, it is around 60 nanometer, let's say, color filter. And if you use sodium, it is around 0.01 angstrom. And if you use laser, it is much, much less than 0.000001. So you can classify the source or you can differentiate the source according to its monochromaticity. And we can determine the monochromaticity by calculating its line. Okay. And another type of properties that we have seen is the directionality of the laser. So we typically say the lasers are highly directional. That is, they travel in a straight line. But in actual situation, what we'll see, there is a small divergence angle. So this divergence angle, it is delta theta. Okay. So this delta theta, it defines the what is the directionality of the laser you have used. Okay. And typically for a helium neon laser that we use in lab experiment, the delta theta, which is the directionality, it is in the order of 1 milliradian. And if you recall, 1 radian is nothing but 57 degrees, right? So the delta theta for a helium neon laser is 1 milliradian. So the delta theta is very, very small. That's why we tell it almost travel in a straight line. And if you want to find out what is the delta theta, what is the divergence after traveling through a length 100 meter, let's say you are using the helium neon laser and we want to find out what is the divergence. So we can calculate it by multiplying the length with delta theta, right? So for L equal to 100 meter and delta theta of 1 milliradian, we see the divergence is around 10 centimeter. Okay. And for L equal to 1 kilometer, the D will be around 1 meter. So this is shown in this schematic. And for a laser, now if you use a laser which is a delta theta of 10 to the minus 7 radian, which is much less than 1 milliradian, then we see that after traveling through this distance, what will happen? The D will be 50 meter. So to define the directionality of the laser, what we do, we calculate its angular divergence, which is also a measure of directionality. And the laser is highly directional. When we say the laser is highly directional, we mean that the divergence angle, it is much, much less. So the small delta theta will define highly directional beam. And another property, it is high intensity. So you must have here, whenever you do experiment, uh, they tell you don't see the laser directly through your eyes. So don't look at directly at the laser. So this is because the lasers, whatever source laser you are using, these are highly intense. So intensity by definition, it is power per unit area. So if you see, if you compare, let us take a laser system. So if the laser is power output is 10 microwatt, 10 milliwatt, and yours and the directionality, the D is around 2 millimeter, then you can calculate the intensity, that is power per unit area. So if you see, and for a fundamental mode, so if you see the fundamental mode, the energy is concentrated. It is nearly circular. So we can take the area as pi r square. So if you put it 10 milliwatt divided by pi r square, then what we'll see, the intensity is around 3000 watt per meter square, right? So you can see how intense these laser beams are, and that is why they advise you to don't look to not look at the laser directly through your eyes. Okay, and another properties which is coherence, right? So coherence by definition, it means the phase relationship among the component wave comprising a laser wave. So if you see, whenever a stimulated emission happens in a system, so you have a, let's say you have levels, which is level 1 and level 2, where the stimulated emission or lasing action is going on. Then whenever the atom it de-excites from this higher level to the lower level, so it emits this radiation over a certain time. So this is fine for finite duration, it emits the radiation. And if you recall, this radiation, uh, which is particular phase relation, it will be affected whenever there is a collision in the system. So, if you recall the collision broadening, it will change the phase relationship. So, we have another parameters also that will affect this phase. So, if you see, these are the phase diagram where the these are three phase diagram of a atom whenever it de-excite from the higher energy level to the lower energy level. So if you see these two uh, waves, so if you see only up to this time, this is the phase relationship is constant, and after that there is a abrupt change in the phase because of some reason like collision broaden. Okay, and when we say the laser is highly coherent, that means it maintains the phase relationship over a significant amount of time as compared to the daily source that we have used. So to define or to quantify the coherence, what we use coherence time or coherence length. So tau C and LC, they define the coherence of a laser. Okay. So coherence time, uh, uh, and this is by definition, it is the average time duration over which the constant phase relationship among the component is maintained. So let's say you have, if you see this figure, only over this time there is a constant phase relationship, and after that there is a abrupt change in the phase in both sides. So for this, what we can do, so we can also define what is the coherence length of this laser, which is LC equal to C tau C. Okay, and tau C, if you recall, tau C is nothing but 1 by delta nu. So delta nu is the line width of the source, and to express LC in terms of lambda, what we can do. So you know this relation. This is the fundamental relation between mu and wavelength, which is mu equal to C by lambda. So when you take a derivative, it is so take the mod because it is so we are calculating the time. So delta nu will be C by lambda square delta lambda. And for coherence length, we can multiply velocity, which is C, with the coherence time to calculate what is the coherence length of this of the laser source that we are talking about. Okay, so LC we can write it in terms of lambda is lambda square divided by delta lambda. And if you compare two sources like sodium lamp and helium neon laser, so for sodium lamp, the delta lambda it is 6 angstrom, and lambda. So if you recall it, lambda of sodium lamp, it is around 600 nanometer. So we take 6 into 10 to the minus 5 centimeter. And if you calculate it using this relation, so we got the coherence length is LC equal to 0.6 millimeter. Okay. And for helium neon laser, what we have delta lambda is around 6 into 10 to the minus 3 angstrom, and lambda, let's say we are taking the same wavelength so that we can compare what is the delta lambda. So lambda is 6 into 10 to the minus 5 centimeter. So for this, if you calculate using this formula, so what we got LC is around 60 centimeter. So you can see the LC for the laser, it is greater than LC of sodium. So that means the laser source can maintain a constant phase relationship over a laser length as comparison to the sodium lamp broadline source. Okay, so that is why we use laser to study the interference experiment. So this is all about what is the characteristics of laser. Then we have seen what are the longitudinal modes of a laser. So we have calculated these. So if you see, these are two mirrors, and there is active, and the light is constantly moving back and forth inside this two mirrors. Okay, and depending on the phase relationship, we calculate what is the resonance frequency, which are also known as longitudinal modes of this laser resonator. So for this, what we have done, so for constructive interference, we require round trip phase difference should be a integral multiple of 2 pi. And the round trip phase difference, if you recall, phase difference is nothing but k times path difference, right? And k is nothing but k0 into n, the free space wave vector into refractive index. And the path difference, it is nothing but 2L. If L is the separation between them, then path difference will be 2. So we have calculated what is the round trip phase difference, and we have equated to the phase, which is Q multiplied by 2 pi. And from this relationship, we have calculated what are the longitudinal modes of this system, of this resonator, which is UQ equal to Q times C by 2NL. So these longitudinal modes, you can also call it as a cavity mode because these are happening inside the cavity. And by taking the next higher order mode, which is nu Q plus 1, we have calculated what is the separation between two conjugative modes. So if you have different modes where the cavity will resonate, so the separation between them is nothing but the free spectral range. Let's define the separation between them. And this separation, which is the free spectral range, it comes out as C by 2NL. Okay. So you can see the new F, it is inversely proportional to L. So that means if you want to increase the separation between them, then you have to change the length. You have to decrease the length so that you can increase the separation between them and vice versa. Uh, After that, uh, cavity modes by theoretically we assume we'll get straight lines in the spectrum at nu q plus 1 and nu q plus 2. But in practical situation, what we have seen, these resonance frequency has certain line width. So these are the actual scenario that we see in the practical system. Okay, and this the line width of this cavity modes, it depends on the losses inside this resonator. So the if you want to get a sharper resonance, then we have to decrease the losses in the system. Okay, so by looking at the cavity modes, we can assume how lossy the system will be. So if the system is broader um, resonance frequency, that means the losses in the system is high. And if it is narrower, then the losses in the system is much less than the first system. And this we have already seen, these are the longitudinal modes, and this is the free spectral range between the, that is the separation between this nu q and nu q plus 1 mode. And for a helium neon laser, if you calculate what is the nu f, the separation between the modes for length 30 centimeters, so what would say the nu f will come around 500 mega. And this FSR, this nu f, it will determine what is the number of oscillating longitudinal modes in the cavity. So we have seen nu f is inversely proportional to length. So if you want to oscillate only one longitudinal mode, so then we have to we have to decrease the length so that the separation between them will increase. And if you want to oscillate it, like if you want to achieve multi-frequency resonance, then multi-frequency oscillation, then we have to increase the length so that the free spectral length it will decrease. So free spectral lengths also determine what are the number of longitudinal modes that will oscillate inside the laser cavity. Okay, and this is the typical gain curve we see in a practical system. So um, so uh, so if we have a gain curve like this, so this is the gain curve for a system, and we have cavity modes that are separated by free spectral range. Now, among these cavity modes, only the modes that have gain that is greater than the loss in the system, that modes only oscillate inside the laser cavity. So if you see, this is the red line is the loss line of the system, loss line of the cavity. So the modes that will oscillate inside the cavity will be only these three modes. Because for these three modes, the losses in the system is lower than the gain in the system. So the oscillating, if you want to achieve what are the oscillating mode in the system, oscillating modes inside the cavity. So please look at what is the gain curve and what are the cavity modes that is crossing the loss line. Okay, and these mode, what they will do. So because we have three modes that are that have loss line that is lower than the gain curve. So these three modes, what they will do, they will increase the bandwidth of the system. So because of the multi-frequency oscillation, what we'll see eventually, the bandwidth of the system will increase, right? So these are the same curve like multi-frequency oscillation. These are the cavity modes, right? And we have a gain curve like. So if loss is around this, then we'll see multi-frequency oscillation. But if you want, let's say you want a single, you want to oscillate only one longitudinal mode. So for that, what we can do? So one thing we have seen, we can change the cavity length, that is the FSR. We can play with the FSR parameters so that the laser cavity will oscillate around one longitudinal mode. And other thing that we can do is that we'll see now. What will the other procedure to see a single frequency oscillation? So as we have seen, multi-frequency oscillation, it will lead to laser source bandwidth. So for many applications, we require single frequency oscillation. So for this, what we can do? So let's say we have a gain curve like this, and these are the laser, right? And this is the initial situation where we have multi-frequency oscillation. So around three frequency will oscillate whenever there is a loss line around this gain curve. Now, instead of this loss line, let's say we have a loss line above this gain curve, so which is the red one. If you see the red curve, so if you see this red curve, this one, so for this kind of loss, longitudinal mode will oscillate inside the cavity because whatever gain that is achieved in the system, it will be lost due to the cavity loss in the system. So if you have a loss line like this, then we don't have any longitudinal mode oscillation. But let's say we have a loss line which is flat around this region, but there is a decrease in the loss around this frequency. So around this frequency, if you see the loss, the gain is greater than loss. So this means now only this mode will oscillate inside the laser cavity. So to achieve a single frequency oscillation, what we can do, we have to see a system where the loss line is high around other frequency, but it is low around the particular frequency that we want to oscillate. So for this, what we do, we use intracavity Etalon. So Etalon, in a simplest term, it is nothing but it consists of two parallel mirrors. Okay, consists of two parallel mirrors where light, when you incident a light, let's say you are incidenting light like this, so light will consist. So as Etalon, it consists of two parallel mirrors. So what will happen? So light will oscillate. It will reflect it back. It will be oscillate inside this Fabry-Perot filter. 1 minute. So it will oscillate inside this cavity. So if you see this figure, so the incident light. So the incident light, it will reflected back and forth between these two parallel mirrors, and some of the light it will transmitted out from this mirror. And depending on the separation between these two mirrors and the angle theta, what we'll see transmission peak in the system. So if you see this figure, so there are transmission peaks around some frequency, and this frequency is given by this relation. Okay, so nu p for the Fabry-Perot Etalon, nu p, it is so this determines the frequency where we see a peak in the transmission. So nu p is p times c by 2mt cos theta, where p can be an integer in the system. And t is the spacing between the Etalon. So this is the t. So t is the spacing between the Etalon. And if you see the practical values of t is around some millimeter. So that means the T for the Etalon, it is much less. So this indicates that the free spectral range for this Etalon, it will be larger than the free spectral range of the cat. So if you see the spectrum, see these peaks are more widely separated. Okay, so that is why we'll take a Etalon for this system. So it's like FSR. FSR for, so if you recall, nu f is inversely proportional to length. When you decrease it, nu f will increase. So for this, we are using it alone so that you can filter out only the, we can oscillate only single frequency uh, in the cavity. So let us see how this is achieved. So this is the gain curve we have seen earlier. So to achieve a single frequency oscillation, we want a loss curve like this. So around other frequency, the loss is high, but around the frequency that we want to oscillate, the loss is much less. So for this frequency, the gain is greater than the losses in the system. And the cavity will now oscillate around this frequency, let's say mu q. Okay. So now let us see how these losses are achieved and how this low loss is achieved in using a intracavity ethanol. So for ethanol, we see that the transmission, it is transmission will be high around frequency where mu, sorry, not mu q. So let us say another index mu p. Mu p will be 3 times c by t cos t. So around this frequency only, the ethanol will transmit the light, and for other frequency, the intensity will be less. So that means around mu p, the loss is less. But for frequency, which is other than mu p, what will happen? The loss will be high because the transmission is low. Okay. So let us see this spectra of the ethanol. This is the spectra that we typically. So let's say this is the Fabry-Pérot ethanol, right? So these are the frequency around which the transmission is high. And if you oscillate, now if you use this Fabry-Pérot ethanol, let's say we are using it around nu q. Okay. So for this, what will happen? Only this frequency. So let me take different color. So only, so if you see the loss curve is like this, that means only this frequency, that is the frequency around this ethanol, it will transmit the frequency sold. And for other frequency, the transmission is around zero. Okay, the transmission is zero, that it is nearly zero. So that means that frequency will be, they will experience losses inside the ethanol and they will not oscillate inside the cavity. Okay. So in this way, by using it alone, we can achieve a single frequency oscillation. So this is the result that we'll get after using it alone. So without it alone, we have a multi-longitudinal mode laser. That is, the laser will oscillate at multiple frequency. But when you use a it alone, what will happen? Only one mode will oscillate inside the laser cavity. Okay. So this is all about the first part of the week 9. So let me ask whether you have any doubt up to now. Otherwise, I will move to the next part. Okay. So let us move to the next part then. So in the next part, so these are some properties that we have seen earlier also, which one is the monochromaticity of the source, which is defined by the line width of the system, which is delta nu. And for a helium neon laser, we see delta nu is around 10 to the 10 hertz. And if you calculate what is the delta lambda corresponding to this delta nu, will come around 10 to the minus 1 angstrom. And for a single frequency laser, the delta nu is around 10 to the 6 hertz and delta lambda is around 10 to the minus 6 nanometer. So you can see how narrow this line width is for this laser. And the second thing we have seen is the coherence time. So coherence is how up to what length and up to what time the laser beam, the emitted wave is maintaining the phase. So, and we quantified this coherence by coherence time and coherence length. So coherence time is TC is 1 by delta nu and coherence length LC is C times TC. Okay. And for a multimode laser, which is delta nu around 10 to 10 hertz. So if you recall this, if you put it in this position, then you calculate TC for the multimode laser is 10 to the minus 10 seconds. And for a single mode laser, which is delta nu in the order of 10 to the 6 hertz, then the TC will be 10 to the minus 6 seconds. Okay. And similarly, if you want to calculate what is the coherence length is nothing but C times TC. So by putting the value of C, you can calculate what is the coherence length for the multimode laser and for the single mode laser. And for multimode laser, it is around 3 centimeters. And for single mode laser, you can see the coherence length is higher than the multimode laser. It is around 300 meters. And this is the definition for TC, which is the average time interval between the time where the phase relationship is maintained. Now we'll see the divergence angle, which is defined by theta, right? So if you, let's say the beam is, we are studying the beam from the waist of the beam, where the diameter is small. And the diameter at the waist is 2 times WZ, right? And as the beam propagates, what will happen? If you recall, the radius of curvature as well as the spot size of this beam, it will change as you as you move away from the waist. So if you see at different positions, Z0, Z1, Z2, they have different radius of curvature of this beam as well as the spot size of the beam. And Z0, if you recall, it is the Rayleigh range. So Rayleigh range is the position where the ROC is minimum. Spot size is minimum. So this is the relationship between the spot size with distance Z. So WZ, it is the spot size, and W0 is the spot size at the waist. So this relation we have already seen, and Z0 is the Rayleigh range where the radius of curvature of the of the beam is minimum. And for larger Z, you can neglect this one because Z square dominate over the one. That is why for larger Z, we have W0 as WZ is W0 Z by pi W0 square into lambda. So now let us calculate what will be the theta angle using this spot size. So we can take the spot size at different positions, Z1 and Z2. Then we can relate it through the angle theta and we will calculate what is the divergence angle. So if you take the difference between the spot size here and the spot size here, and spot size here. So what will happen? The angle theta. So WZ2 and WZ1, it will give lambda by pi W0 Z2 minus Z1. And this you can relate it through the tan theta. So tan theta will comes around lambda by pi WZ, right? So and for smaller, if you are taking a laser that has smaller divergence angle, that means the theta is small. So for this case, we can approximate tan theta as theta. So theta will come around lambda by pi WC. And if you put some practical parameter, let's say we are taking lambda as 1.5 micrometer and pi is 3 and W0 is 0.5 millimeter, then we see theta will come around 1 milliradi. So this we have seen, this is the divergence angle for a helium near laser, right? And so this is the relationship between what is the how the spot size is varying with respect to Z. So when you consider higher Z, larger the distance from the waist, then we see a linear relationship between the spot size and the distance Z. And next we'll talk about what is the beam diameter. So at waist, the beam diameter is 2W0. This we have seen earlier. And W0, this we are seeing again and again. W0 is root over of Z0 lambda by 5. Now, if we take, let's say, the resonator we are studying is a confocal resonator. So for this, if you recall from week 7 content, then Z0 we have calculated as Z0 equal to L by 2. And if you put some practical value, let's say L is 20 centimeter, then we calculate what is the spot size at the waist. It is around 0.14 millimeter. So this is the beam diameter at waist for a practical laser. Okay. Now, when we in a lab experiment, when we use laser, then we use some lenses to focus the spot, right? So for this case, if you want to find out what is the diameter of the focus spot, then for this, you can use this relation. So D is given by F lambda by D. Okay. So this is the diameter relation of a focus spot. So this we have, you can calculate it from this single slit or array pattern. Okay. So if you see the single slit pattern, so we see central maxima where the intensity is more, and we see minimum around this central maximum. And the angle at which we see the minima, it will come around lambda by D, right? So this is the angular diameter for this minimum. And let's say the lens have focal length f. So that means if you see a schematic, so this is the point where the laser spot is focusing, and this is the minima point. Let's say this is the minima point. So that means the diameter. So if you want to calculate, uh, so let me draw again. It's not continuous inside this. So to take a lens, so this is where the laser spot is focusing, and we know what is the position of this, what is the angular position of this minima, which is theta equal to lambda by d. So if you want to calculate this point, then what we have, we can multiply by f, right? So that means this is given by f lambda by d. So you can calculate it from single slit or array disk. So array disk where to give a brief introduction. So when you pass a plane mirror, when you focus it using a lens, then we'll see a circular pattern in the system. So and for the central spot, we see that the theta will come around 1.22 lambda by d. Okay. And these are some values, that is by using some values, if you calculate what is the diameter. So diameter, it will come around 1 micrometer. Okay. It will come around 1 micrometer using it. Yes. And next part is what is the intensity. So intensity, we have seen it is power per unit area. And if let's say we have a photodetector like this is the active region of the photodetector. And if the beam it is falling inside this active region, then we can say the power of this laser it is independent of Z. So whatever Z will be, the power will remain same if the beam is falling inside the photodetector active region. In contrast, if you see the intensity pattern, so intensity pattern it depends on the Z because as the beam propagates, it, the radius of curvature as well as the spot size it changes with respect to Z. You see this, and if you want to find out what is the intensity at along this line, then you can see the intensity is gradually decreasing as we move towards higher value of Z. So that means the intensity is depends on the Z because spot size it depends on the Z. And if you want to calculate what is the power, if you are given intensity, then you can integrate it over the cross section to calculate the power. So now we'll see some of the example. The first one is the fundamental mode where both n equal to 0 and m equal to 0. If you recall this, shows a Gaussian pattern, right? And for TM00 mode, we have intensity I00 RZ, and this is given by this formula I0 spot size plus square, and there is a exponential term. And now we know the what is the intensity distribution of TM00 mode. And if you want to find out what is the power, then we have to integrate over the active region. So let's say the power P0 you want to calculate. So as if you recall for TM00, as we move away from the center, the intensity gradually decreases. So as R increases, the intensity gradually decreases. So that is why we have taken integration from 0 to infinity. And this is the cross section of this circular cross section, R d theta dr. And if you integrate it, you will calculate what is the power P0, which will be nothing but P0 equal to I0 by W0 square by 2. So after doing integration, we'll get a intensity I0 as 2P0 by pi W0 square. And if you put the value of for a Z for this is for I00, right? And for a non-zero value of Z, we have the intensity of this I00 mode will be 2P0 by pi W0 square, W0 divided by WZ square. And WZ, if you recall, this is related to W0 by this formula. So if we put it, we will get a formula like this. So I00, you got the I00 intensity as I0 divided by 1 plus Z by Z0. Good. So this shows how the intensity varies with Z. So if you put Z equal to Z0, which is the Rayleigh range, then the intensity at Z equal to Z0 will be I0 by 2. So this shows how the intensity evolves with respect to Z. And if you want to find out the power, then so we have to. So this is over. We have integrate it over R equal to infinity. But instead of R equal to infinity, if you want to integrate over a finite region, let's say we want to find out what is the power over a distance R0. So if you see the red line, we want to integrate over this region. Instead of 0 to infinity, we have 0 to R0. And if you calculate it, the PR0 will come around this formula. And you can put different value of W0. Let's say R0 is equal to the spot size W0. So for this case, if you calculate the fractional power, then the fractional power will come around 85%. And if you take another value of R0 where R0 is 1.5 W0, then we'll see the fractional power will now increase, which is 99% of the incident beam. Okay. So this is all about the laser beam. That is the laser beam diameter, what is the power, how you can calculate the power, and how you can calculate how the intensity varies with respect to Z. Now we'll move to our next part. So these are some of the, so after going through all this content, I will solve few problems which I haven't solved in the previous live section because of the time constraint. So let us quickly go through this concept. So till now, do you have any doubt in any of this slide? Okay. So let us move to our next part. So next part is this we have seen earlier. This is the we have seen the multi-frequency oscillation. It will increase the source line width, and for application where we need single frequency oscillation, then in that case we can use intracavity tunnel to filter out a single frequency or to oscillate the laser cavity at a single frequency. So use of laser cavity, it will lead to single frequency oscillation. And these are some of the information about what is the how, where we'll get the transmission peak for the antenna, which is given by this form. And from this, by using the etalon, we have seen we can oscillate the laser cavity at single frequency. So this we have already seen earlier, so I'm not going to cover this part. So now we'll see. So initially we have seen how to filter out one single longitudinal mode. So now we'll see if you want a particular pattern. So if you want a, let's say you want a Gaussian pattern like this for a particular application, or you want a pattern like this, then how you can achieve this? So instead of a longitudinal mode, how you can select single transverse mode. So transverse mode, it means the filtering distribution. So filtering out single transverse mode means we are filtering out, we are selecting those modes which have same field profile along the transverse direction, either this or this or any kind. So for this, what we can do is, so in the longitudinal mode selection, we use intracavity tunnel. For this single transverse mode selection, we can use intracavity aperture. Okay, so now we'll see how you can use this to select a particular beam pattern. So this we have already seen earlier. So these are the allowed solutions, which is Hermite Gaussian function given by this expression. And for a fundamental mode, which is for fundamental mode L equal to 0, M equal to 0. So for fundamental mode, we found the intensity will be given by this expression, which is a Gaussian pattern because of this factor. So now, let's say you don't want to you don't want to select the TM00 mode. So for this, what we can do, so we use intracavity aperture in terms of, let's say we use metallic wire or grid or Teflon aperture. So if you recall the lecture, so for metallic wire, so according to the boundary condition, at the boundary, the tangential component of electric field will be 0. So now if you use this metal, let's say you have laser cavity where the TM00 mode is oscillating. So now if you put the metallic wire in this direction, then what will happen? Because of the boundary condition, so because of the continuity of boundary condition, this TM00 mode will experience a loss because the tangent, the electric field is 0. But if you put the same metallic wire in this direction, then there will be no loss in the system for this mode, right? Let's see the higher order mode. The next higher order mode where L is 1 and M is 0. So for this case, you can recall this is the contour plot of this mode where we have two peaks around the origin. So for this case, if you put the metallic wire, let's say in the transverse direction, then the losses in the system for this mode will be 0. But if you put the same metallic wire here or here, then we'll see a losses in the system. So this is the same explanation that I have told. So this we have put metallic wire in this position, then we'll see no losses in the system. But if we put metallic wire in this direction, then we will see losses in the system because of the continuity of boundary condition. So the intracavity aperture in terms of metallic, in the form of metallic wire, can be used to give losses to particular mode in the system. Let's say this is the analogy that I think everyone has understood what this means. So let us see, we have a higher order mode where the pattern is like this. So for this case, if you want to select this mode, then what you have to do, we have to place the metallic wire in this direction and in this direction. So for this direction, the TM00 mode will experience a loss. If you see, so if you see this figure, the TM00 mode will experience a loss. And for this metallic wire, for this one, the TM01 will experience a loss. But the this mode, if you recall, if you calculate what is the mode of the system, so if you see there is 1 0 along this direction, 1 0 along y direction. So that means this is TM11. So the lower order mode TM01 and TM00 will be filtered out, but the TM11 will be selected if you use this aperture in the system. And for if you particularly want to filter out TM00 mode, then what do? We use Teflon aperture. So if you see the field pattern of this TM00 mode, then this field pattern is like this, right? So this is the gain curve. So let me show the field pattern. So field pattern is like a Gaussian curve. Now if you put a aperture here, so what it will do? It will filter out, it will select this mode, will easily pass this mode. But other modes, it will be blocked. Like, so let me show a graph here. So this is TM00, this is TM01. So because of the phase break, it's not possible to draw in one. So let me draw anywhere. So if you see, so let us take two graphs. It's better. If you see the TM00, this is fill pattern is like this, but TM01, the fill pattern is like this. Now, if you put a aperture here, this mode will easily selected, but this mode will be blocked because of the aperture in the system. So this is how you can use Teflon aperture to select one single transverse mode in your system. And these are this we have seen earlier, I think. This is TM00, 010, 20, 30 in the system. So you can go through this field profile to calculate what are the nodes in the system and how you can select one mode over other using either Etalon or using either aperture in the system. So, so we have come to the last part of week 9, which is the ultimate line width of the laser. So before that, let me ask whether you have any doubt up to now. Okay. Okay, then let us move to the next part. So this is the last concept that we have seen in week 9. So if you recall, for without the Etalon, we have multi-frequency oscillation. So let's say we have a laser source, which is line width, which is spectrum like this. The line width is given by full width at half of the maximum. And for this laser source, let us uh, assume we have a gain curve like this. So for this gain curve, what we can define various parameters. One is laser bandwidth. So laser bandwidth is this region B. So this indicates the region, indicates the frequency width within which the loss line of the gain of the frequency is greater than the loss line. So you have different cavity modes, right? These straight lines are the cavity modes. So you have different cavity modes, and for some cavity modes, like this cavity mode and this cavity mode, the losses is much greater than the gain. So that means they will not oscillate inside the cavity. But for these three, the loss line is lower than the gain curve. So that means we will see a amplification using this of these cavity modes. So using this, how many number of this cavity mode is passing through this laser, then we define a laser bandwidth, which is D. And another term is the line width of the laser transition, which is full width at half of the maximum, delta nu. And for the cavity modes, we also have line width because these are not sharp peaks. These have some line width, and we define the line width of this cavity resonance as delta nu. So delta nu is the line width of the cavity resonance. So now we'll see. So we have seen how we can achieve single frequency laser using the intracavity Etalon. So for a single frequency, so we see if you so let me go back to this slide. If you see, without Etalon, we have more multi-frequency oscillation, and with Etalon, we see that only this frequency is oscillating inside the laser cavity. So now we'll see whether the laser. So this cavity is defined by delta nu, right? This cavity resonance is defined by this line with delta nu. So now we'll see whether the laser that we are operating is also having the line width which is equal to the line width of the cavity resonance. So we'll see now whether this delta nu and delta nu laser is equal or not. So for this, we will take some practical examples, some practical values so that we can compare these modes. So for a practical laser, for a single frequency semiconductor laser, we have delta nu is in the order of 10^6 to 10^7 hertz. And if you recall, for cavity, delta nu is given by 1 by 2 pi Tc. So please remember this small formulas because this will be useful to calculate the to solve the problems. So this will not be provided in the exam, in the final exam. So delta nu, if you recall, it is 1 by 2 pi Tc, and Tc it is given by n by C alpha r. And if you recall alpha r, it is the resonator loss coefficient, which is given by alpha C and 1 by 2L ln 1 by R1 R2. R1 R2 will be given in the system. So if you take a typical value of alpha C and alpha m, so alpha C is in the order of 1 centimeter inverse and alpha m it is in the order of 40 to 50 centimeter inverse. So we can for a calculation purpose we can neglect this parameter, and for using these values what we have seen, the delta nu for the cavity resonance will come around 3 into 10 to the power 10. So that means this single frequency delta nu is 3 into 10 to the power 10 hertz. But delta nu laser, we see it is in the order of 10 to the 6 hertz. That means delta nu laser is much smaller than the delta nu cavity. So what are the reason behind this broadening of this cavity resonance? So the one of the reason, so in practical situation, what we assume whenever there is a steady state, there is no losses in the system. So that means the TC, that is TC, what is TC? This is the time at which the energy will fall down to 1 by E times, right? 1 by E of its initial value. So because there is no losses in the system, the TC will be infinity. So for this case, we assume we'll get a delta nu is 0. That means we'll see star peaks here. But instead, in practical situation, we see delta nu is much greater than 0. It's not small. So the factors that will affect is one is the temperature fluctuation, and another is the dimensional uncertainty, and another one is the spontaneous emission process. The temperature fluctuation, so if you recall, it is embedded in direct refractive index. So the refractive index will change with respect to time. So with respect to temperature. Mm. So the delta nu, it will change with respect to temperature. And because of the change in delta nu, so if you recall the cavity resonances, nu is given by Q, C by 2NL, and delta nu, if you calculate, it is delta N by N plus delta L by L. So when the temperature changes, the refractive index changes. According to that, the delta nu will change. Or whenever there is a uncertainty in the cavity length, then we see a broadening in the line width of the cavity mode. So let us take some examples so that we can calculate what are the practical values. So for frequency, nu 10 to the power 14 hertz, and if you want to achieve a delta nu of 1 hertz, then for that you can see the delta L, it should be 10 to the minus 30 centimeters. So you can see the variation in the length should be small so that such that the delta nu, the line width of the cavity mode will not be affected. That and the temperature, as I have said, temperature also contribute to the line width. And now we'll see how the spontaneous emission it will affect the laser line. So if you recall, um, for the spontaneous emission, these are emitted uh, along. These are not directional, so these are emitted along various different directions. So this spontaneous emission, if they couple to one of the cavity mode, what will they do? It will change the phase relationship. So initially we have phase like this, let's say. So it will introduce a random phase fluctuation in the system. And because of this random phase fluctuation, we'll see a broadening because of the coupling of the spontaneous emission to the one of the cavity mode. So because of that, we'll see a broadening due to the spontaneous emission. So now we'll calculate how we'll quantify this broadening due to the spontaneous emission. And this we can, so let us assume the spontaneous emission, it is coupling to the cavity mode, which is frequency around nu zero. And we want to calculate what is the delta nu sp around this frequency nu zero. So for that, let us define what is the, so if you recall the line width or the losses in the system, it is also quantified by the quality factor of the system. So for the spontaneous emission around this frequency nu zero, if uh, if we define the quality factor, it is nothing but nu zero by delta nu sp. And the formal definition of quality factor is 2 pi nu zero energy stored in the resonator divided by rate of change of energy due to the spontaneous emission. So now we are only seeing the spontaneous emission part. And let us say we have for a particular time we have n number of photon in the system. Then the energy stored around this frequency nu zero will be n s nu zero. So we have calculated what is the energy stored in the resonator. So now let us see what is the rate of change of energy due to the spontaneous emission. So if you recall, the rate of spontaneous emission, if you have a system like this, where the lasing is happening between these levels, then the rate of spontaneous emission, it is given by k times n2. It is given by k times n2. And k is this constant. K is defined by this value. And N2 we have already seen earlier, it is n by n plus 1 by kT. And for a steady state, the n is very large. So we typically take n plus 1 is n. So that means the N2 is 1 by kT. So now we can easily find out what is the rate of spontaneous emission, which is k times N2, and N2 is 1 by kT. So k into k by Tc. So that means the rate of spontaneous emission is given by 1 by Tc. So this is the rate of spontaneous emission in the cavity mode. And if you want to find out what is the energy, rate of change of energy, then we have to multiply it by the energy H nu zero. So we have already calculated what is the energy stored in the cavity, which is NH0, and what is the rate of change of the energy due to the spontaneous emission. So now we'll put some another parameter. Let's say we are given P out. So P out, if you recall, it is given by NS0 divided by T. And this, if you recall, this we have already seen earlier. And we typically neglect this Ti term because it is much less for a practical system. So from this, we calculated one parameter. So we calculated the numerator part is NS0 equal to P out times TC. So that means TSP for spontaneous emission now is given by nu 0 divided by delta nu SP. And by putting all of this value, we can calculate QSP as this term. So these are the QSP for the spontaneous emission. And delta nu, this is 1 by 2 pi TC. That means TC is 1 by 2 pi delta nu. And if you take nu 0 and delta nu SP that we have calculated using equation 3, so if you put it, then what you will see, the delta nu is given by delta nu SP is given by this term. This is the ultimate line width of the system. And if you see delta nu, it is proportional to the delta nu square, and it is inversely proportional to the power output through the laser cavity. But this we have derived it using some approximation. For accurate answer, what we have seen, the delta nu is given by this term that we have seen earlier and multiplied by a factor n2 divided by n2 minus n1 at threshold condition. And this factor, it typically lies between 2 to 6 depending on the output power. So let us see some graphical variation of system. Uh, so this is the graph between delta nu laser versus the power output. So if you see, sorry, 1 by P output. So this should be linear curve because delta nu, it is inversely proportional to P. So if you see, the curve is almost linear. And as temperature increases, the slope is also increased. And it is not typically we assume when delta nu is 0, then it should be when P out is 0, when P out is 0, we assume delta nu SP should be 0. But because N2 is proportional to P out, we see there is a non-zero term, non-zero value around this intersect point. Okay. And so this is the example. Let's say we have P output as 1 milliwatt and delta nu is 10 to 10 hertz and lambda this value. Then we can calculate what is the value of mu 0. Then we can calculate what is the line width due to the interference of the cavity mode with the spontaneous emission. So which will come around 80 kilohertz, and for laser it will come around 10 megahertz. You can see the laser is broader than the line width due to the spontaneous emission. And this is for the helium neon laser. So if you calculate using these values, then you can see the delta nu SP, the broadening due to the spontaneous emission is delta nu SP, and this is the broadening we have seen in the laser final system, which is 100 kilohertz. So you can see this is much greater than the line width due to the spontaneous emission. So this covers up what we have seen in the week 9 content. So let us now solve few problems that have skipped in the last section. So till now, do you have any doubt? Otherwise, let us see few problems that I was planning to solve in the last section. So please go through the assignment, the concept, because in the final exam, some of the problems will be assignment based. So please go through the problems as well as the additional problem that I'm solving in the live section. So let us see whether you are able to recall what are the concepts and able to solve the problems that I'm going to solve now. So let us see the first problem. So the first one is, which one of the following must remain same after one round trip of a transverse mode of a optical resonator? So the first option is energy of a mode. Second is field distribution of a mode. Third is amplitude of a mode. Other one is the phase of a mode. So what will remain same? So if you recall, whenever the laser propagate, it oscillate back and forth between these two mirrors. Then both the amplitude, that is, both the amplitude, it will decrease. It will vary with respect to z. And after one round trip, what will remain same? The only the field distribution of a mode, it will remain same after one round. Others, they will vary after one round trip, because these mirrors are reflecting, right? So some part will get reflected, some part will get transmitted. So depending on the reflectivity, the amplitude, the phase, and the energy, both all the three will change. Only the field distribution, it will remain constant after one round. So this is the conceptual one. So let us see one numerical problem. So the second problem is, it is given the spot size of a diverging Gaussian beam of wavelength 600 nanometer is 2 millimeter at least. So that means what is given? W0 is given to you. It is 2 millimeter. Okay. And the spot size of the beam increases to 4 millimeter after it propagates through certain distance. So it is asking after how long distance the spot size will increase from 2 millimeter to 4 millimeter. So if you recall the relation WZ, it is given by W0 1 plus Z by Z0 square root over half. So it is asking about this Z, and all these three are given, but we don't know Z0. So Z0 is Rayleigh range. So if you recall, Z0 is given by, if I see the formula, it is pi W0 square divided by lambda. And both W0 is given, it is 2 millimeter, and lambda is given, it is around 600 nanometer, right? So use this to calculate what is the value of Z0. Minute. So if you use it, then Z0 will come around 20.94 meter. So now you already know what is the value of Z0. So you simply have to put in the final expression. So W is given 4 is 2 uh, and it is 1 plus Z by Z0 is 20.94 whole square divided by half. So if you square it in both sides, so this will cancel. It will be 2 here. If you square it both sides, it will become 4 1 plus Z by 20.94 whole square. Now, if you rearrange it and take the square root, what we'll get Z equal to root 3 times Z0, which is given by root 3 times 20.94, which is nothing but 36.97 meters. So, this is how you can solve this problem. So, if you remember this formula and the relay range, then you can easily calculate what the question is asking about. So, let's the next one. So, next one is ULM represents the Gaussian modes of an optical resonator. If the field distribution of a particular mode is Gaussian with wave size, so W0 is given is 1 millimeter, wave size 1 millimeter, and the field is Gaussian. So that means it is the TM00 mode, right? Then the numerical value of L plus M plus 1 and the spot size at the relay range are. So L plus M plus 1 you can easily calculate because L is 0, M is 0. So that means L plus M1 is 1. So that means we have two options which are L equal to L plus M equal to 1. One is option A and option C. So now we have to see what is the relay range. So relay range, if you recall, WZ is given by W0 1 plus Z by Z0 square over half. And at Z equal to Z0, we have WZ equal to W0 root 2. So this is root 2 times W0. So that means the spot size at the relay range for this Gaussian beam is root 2 times spot size. Root 2 times spot size at the west. So that means the answer will be A. I think this problem is easy to solve. So let us move to our next problem. So this is asking about what is the transverse mode degeneracy of the resonance frequency, TM2. So for TM32 field distribution, what is the transverse mode degeneracy? So this is given by L plus M plus 1. So for this is the value and this is value of M. So please remember to take the first index as L and the second index as M. So don't interchange the index. So for this case, it will come around 2 plus 2 plus 1, which is 5. So these are some conceptual problems that you have to remember. What is the formula for the transverse mode degeneracy? What is the L and M value for different types of mode? For Gaussian, what is the L and M value? Now we'll move to the next question. So let me read out the question. So the question says, if a stable spherical mirror resonator has waist size of the Gaussian mode located exactly at the position of one of the mirror. Then the resonator is. So it is asking about for what type of mirror resonator system. We see that the waist size is exactly coinciding with the location of one of the mirror. One is on first option is plano concave, second is plano convex, third is convex concave, and last one is symmetric plane mirror resonator. So if you recall, the ROC at, at waist is infinity. If you recall the ROC formula, then at the waist, ROC is infinity. And for what kind of mirror we have infinity radius of curvature? This is for plane mirror, right? So there are two options, which is plane mirror with answer. But one have concave, one is convex. But if you recall plano convex lens, this is not a stable resonator. This forms a unstable resonator, right? So if you recall the diagram, I think this diagram, then you see for only plano concave mirror, you see this forms a stable resonator system. So that means the answer will be plano concave mirror resonator. Okay. So now let us move to our next problem. So this is a numerical problem. So the question says, if a diverging Gaussian beam with ROC of wavefront is 15 centimeter becomes a converging beam. So initially we have a diverging beam like this, but after going through a mirror, it converges back. So initially we have diverging beam with ROC is 15 centimeter. And it becomes converging Gaussian beam with ROC equal to 10 centimeter. That means after reflection, so this is Ri, right? And after reflection, it will be Rr. So Rr is, it is given minus 10 centimeter. Because it's a converging, we are taking Rr is minus 10 centimeter. So it becomes converging and immediately after the reflection from the mirror, then it is asking about what is the radius of curvature of the mirror. So we have a mirror. Initially, the beam was diverging, and after taking a reflection from the mirror, it becomes a converging beam. So if you recall the formula, 1 by Rr is given by 1 by Ri plus 2 by Rn, right? Rr it is given. So please take care of the signs. So the sign will be crucial because you can easily identify what is the mirror, what type of mirror is used in the system. So Ri is nothing but is 15 is 2 plus 2 by Ri. From this, we have to just uh, rearrange the term. That is Rm, it is given by minus 1 by 10, sorry, 2 by Rm is given by minus 1 by 10, minus 1 by 15. And if you calculate the Rm using this formula, then what we'll see, it will come around minus 12 centimeter. So minus means it's a concave mirror And this is the radius of curvature of this concave mirror. Okay. So now we'll move to the next final problem. So up to now, do you have any doubt in the problem? Okay. Then let us see what is our next problem. So the last problem says, if a converging Gaussian beam with ROC of the wavefront is 10 centimeter is incident on a convex mirror of ROC 5 centimeter, then find what is the radius of curvature of this reflected wavefront and what is the nature of the beam after reflection. Okay. So this is similar to the previous problem. So we have to use this relation 1 by RR equal to 1 by RI plus 2 by R. Ri and Rm are given. So Ri is given. You see, it's a converging Gaussian beam with ROC 10 centimeter. So that means it will be minus 10 centimeter. Right? And Rm it is given. It's a convex mirror with ROC 5 centimeter. That means it is positive 5 centimeter. So now just have to calculate what is R, which is nothing but it is equal to 1 by 10 plus 2 by 5. So if you calculate it, it will come around 3 by 10. So RR, it will be 10 by 3 is equal to 3.33 centimeter. And because it is positive, that means the beam will diverge. So we have two options, which is same value of ROC, but because this RR is positive, that means the beam after reflection will diverge after getting reflected from the convex mirror. So these are the problems that I wanted to solve in this lab section. So do you have any doubt in any of these 7 problems? If you have any doubt, you can write it in the chat box or okay. So let me unmute it. So you can speak now. You are already unmuted. If you are not able to speak, unmute yourself. You are already unmuted from my side. Then you can speak or you can ask the doubts you are having, or otherwise you can also write it in the chat box. What is the problem you are having? You have raised your hand. Are you able to hear my voice? In assignment 8, question number 6 or 7. Oh, okay. Okay, I have gone through your queries. So you have doubt in question 6. I think you have calculated it around 0.769. So you have rounded off around 0.77, I think. But they have mentioned to, they have taken a range around 0.56 to 0.76. So this I will, I have already seen your solutions also, the procedures also. This seems to be correct for me. So there is uh, no problems in any of this part. So it seems to be correct, your answer. So let me talk with the NPTEL team for your solution. So we'll get your reply. So please wait for 3 to more some days so that they will update the answer as well as the query. And similarly for I think in question 7 also, depending on the range where we are seeing the profile, you can get a whole bonding either on two hole bonding around the x equal to 0 on one side of x equal to 0 and the other side of x equal to 0 if you take x equal to minus x to plus x. But if you take from x equal to from 0 to x, then you should have four uh, hole bonding in one side. So both are given in the answer and it also seems to correct. But let me talk with them regarding this two question. Other than these two questions, do you have any other query? So these two questions, I will talk with them. Okay. Mm, so we have already covered the week 9 content in this live section. And I have tried to solve a few problems, a few additional problems, so that it will help you to understand to solve few problems for the exam purpose. So please go through the videos as well as each assignment and the week content so that it will be helpful in your exam. So for now, let us end our section. We'll meet on next Saturday, same timing, 4 to 6. So please try to join the live section because during the live section only you can ask the doubts directly to the TS and you can clarify it uh, directly to the TS. And thank you for joining the section. I hope the topics and the concept that I have covered is clear to you. If not, then please feel free to ask me during the live section, or you can write your query in the discussion forum also. So I will try to reply there in the discussion forum, or I will try during the I will clarify your doubts in the live section. So for now, thank you for joining the section. So let us meet in the next Saturday. So goodbye, everyone.